Hey, what's up, guys? Yeah, so today I want to talk about this Jordan Chevalley decomposition, and this Jordan Chevalley decomposition in the linear algebra sometimes is related to a thing called the Jordan normal form. And so this is like usually in the linear algebra is like the final chapter or something. So some of you may not heard about it. Maybe you heard about it, but you don't understand why this is true. So this is kind of the miracle, the most, I think probably the most difficult part in the linear algebra. And why I need to talk about it is because not all the matrix is diagonalizable. So so sometimes you need to like more refined decomposition for any matrices. And also if you notice Jordan normal Jordan Chevalley decomposition, then this will related to the algebra. So in the future I will talk about the algebra decomposition. So I think it's an important one. Okay, so hope you guys subscribe to my channel. You can go to my channel to see whatever you want. Okay, and okay, so let me just quickly remind you. So usually, so all the vector space I said in this video are complex, finite dimensional complex vector space. So all vector space is finite dimensional and complex over a complex field. So simply speaking, if you're not, you can use isomorphic to complex to the power n. Okay. Okay, so the basic the motivation. Let me just talk about motivation. The motivation is that in a linear, let's say you any operator v to v, and if t is good enough, right? So the one is that if you study if t is good enough, simply speaking, is that then t can be diagonalizable. So there are some matrices, some special matrices, which is you can diagonalizable. Diagonalizable means that the eigenspace of T, or sorry, the eigenvector of T will span the whole vector space. Okay, so this is equivalent to the T is diagonalizable because you can find matrices, you can find representation such that this T is maybe lambda 1, lambda 2, up to lambda n. And if you choose the eigenvector to be like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, and you can see that the eigenvector of T will span V. So if eigenvector of T will span V, is if and only if T can be diagonalizable. Okay, so these kind of matrices are somehow like very good. For example, if your matrix is Hermitian or unitary, or sometimes you can normal. Okay, so these are very good. That one matrices you can do the diagonalizable. Okay. Okay, and then there are second spatial type. There are more. There are general. So in general, sometimes the matrix cannot diagonalizable, but you can prove that you can always find a basis such as a matrix upper triangle, upper triangle. Okay, so these are all for all t. Okay, so basically you can find a basis such that the t looks like this, and all these are 0. Okay, you can check out my previous you can check out my video list, linear algebra lecture list. You can find this proof. Okay, so but sometimes this proof is not good enough, right? Because upper triangular is not good enough. So this lead to the so-called Jordan form or Jordan normal form. So basically, any matrix V to V can be you can do the Jordan normal form. Okay, maybe let me just quickly do a very stupid example, but at least will give you the idea. So let's consider V to V C2, and let's say you can calculate it's let's say T. You can calculate a characteristic polynomial. Suppose this characteristic polynomial is T minus I 0. Okay, so obviously that if the characteristic polynomial is T minus lambda 1 and the T minus lambda 2 I 0, then and the lambda 2 is different from lambda 1, and in this case that you can write T in terms of this, because different eigenvalues must have different eigenvalue must have different eigenvectors, right? But if you get the multiple roots, t minus lambda I squared equals 0, there are two possibilities. Okay. So the possibility is that this one can define v of lambda to be t minus lambda 1i. It can define, so this is Eigen Space, means that this. So you collect all the vectors such that tv equals to lambda v. Okay. So there are two possibilities. The first possibility is that dimension of v lambda is 2. Okay. So in this case, that every vectors. So in this case means that the v lambda will just be v, right? So you can pick up the basis. So in this case, t is still diagonalizable. Okay, so it looks like lambda 0, 0 lambda. And there are second possibilities such that dimension v lambda is 1. Right? Dimension v lambda cannot be 0, otherwise it's not eigen. Otherwise it's not eigenvalue, right? So dimension v lambda can be 1. So in this case means that there is this u such that so if dimension v lambda is 1, but we still have t minus lambda squared, on any v is 0, right? For anything is v belongs to v. But t minus lambda, v lambda, right? So v lambda is different from v. Okay, so it means that there is a u such that what? Such that t minus lambda I on u is non-zero, but t minus lambda I square u must be 0. Okay, so you can just write t minus lambda u defined to be v, and obvious that tv is 0. Okay. Obvious that tv lambda is equal to lambda v. This sentence is the same as this sentence. Okay, so which means that in this case you can write, you have a basis such that uv equals to tu equals to lambda u plus v, and the tv equals to lambda v. Okay, so if you write, then in terms of basis, which you guys t equal to lambda 0, 1. Okay, so this is the Jordan normal form. Okay, so which means that in a 2x2, there are only 3 cases. Either lambda 1 different from lambda 2, you can have the diagonalization. If lambda 1 equals to lambda 2 equals to lambda, and the dimension of v lambda is 1, that is 2, then you still have t equals to lambda. Okay, if lambda 1 equals to lambda 2 equals to lambda, but the dimension of v lambda is 1, means that you can have the Jordan normal form. Okay, so this is a very simple example that you don't need anything, right? You just need to do 2x2 matrices and understand the basic. Okay, so in order to, let me just talk about results. Okay. And okay, so what I want to say is that theorem, this is the main theorem that we will prove it. Basically, the Jordan Chevalley decomposition. Is that any operator t, let's use x. Okay, so x can be written as xs plus xn. Okay, such that this guy is semi-simple. Simply speaking, is that xs is diagonalizable. And ss is sn is an important. Okay, important means that there is a m such that xn to the power m to be equal to 0. Okay, and so these two are not so impressed, right? But there are commuting. Okay, you can easily show that if you're smart enough, right? You can easily show that someone gives you these 3, then you can prove that by carefully choosing the basis, you will get a Jordan normal form. By carefully choosing basis. Okay, so now the proof is very not so trivial. Okay. Right, so there are different kind of proof, right? One is using, if you know enough algebra, you can use the module language to prove it, but I'm not gonna do this. Okay, so my the treatment that I want to do is using the generalized Eigen Space. Okay, so let me just quickly say something. Okay. So okay, so let me just introduce the notion of generalized eigenspaces. Okay, so the idea is the following, right? So the idea is that if somebody give you the t as a vector v to v, and then you can calculate polynomial characteristic polynomial. So basically, characteristic polynomial p of t is divided with determinant of t minus on I. Okay, so yeah, it's the so it's say dimension v is n. So this guy will be n by n complex matrices, complex polynomial. Okay. Okay, and so you can do whatever decomposition. Maybe there's a -1 something, and you get lambda minus lambda 1 to the power m1, lambda minus lambda 2 to the power n2, lambda minus lambda n to the power n. Okay. Now you can define a so-called generalized eigenspace. So let me just define P of bracket lambda to be V belongs to V, such that lambda minus band notation. Okay, not so bad. So this means that T minus lambda I to the power m V is 0 for some m. Okay, so this means that this is called a generalized eigenspace. Generalized eigenspace. Okay, so one results which is very important, and I will give the proof is today is that your vector space. This is a theorem. Most important theorem is that this vector space, your vector space, can be written as a direct sum of generalized eigenspace. Okay. So this is lambda 1, lambda 2, lambda to up, maybe up to lambda something. Not maybe lambda m, maybe lambda k. Okay, so this is k. Okay. So this is almost the same as in the if t is diagonalizable. Also, if your t has if t has n distinct if n has this eigenvalue, right? Then in this case, that your v can be written as the span of this eigen value. Okay, so this is a special case of this generalized eigenbasis, generalized eigenspace. So you can prove that by carefully choosing, you will get a different Jordan block if you know this theorem. Okay, so the power of this theorem is that your vector space actually the decomposition of the generalized eigenspace. So let me just write it down. I think it's important. So vector space now can be decomposed or direct sum decomposed into direct sum of generalized eigenspace. Okay, and obviously that if you take dimension v, by the way, your dimension v will be the multiplicity, right? So will be dimension of will be so will be just sum over let's say lambda 1 corresponding to m1, lambda 2 corresponding to m2, lambda k there is mk. Okay, so this will be just m1, m2, mk, right? And there are some, so m1 plus mk will be m, because this is n by n matrix, sorry, n complex degree n polynomial. So this will be mi I round 1 to k, which is n. So this proof is trivial, right? Because but you need to prove the dimension v lambda is m1. Okay, so maybe you need to spend time to prove, but it's not difficult. Okay. So so my maybe in this video, let me just do this. Okay, so suppose previous statement is true. So suppose the eigenbasis, right? The vector space can be decomposed into the generalized direct sum generalized eigenbasis. Previous is true. then this Jordan Chevalley decomposition is easy to prove. Chevalley is very easy to prove. Okay, so let me just prove this, and maybe in the next video that I prove this main theorem. So this is the next. Maybe let me just next videos. Okay, so this is next. Okay, so suppose previous statement is true, then it will be very trivial to prove this theorem. Okay. The idea is right. We first define S as XS, right, to be V to V. By the way, let me just use X as a linear operator. Okay, it's very easy to show, right? So I can define now I can write V to be direction of VI. Okay. Maybe I from 1 to K. And each VI is each VI now is a generalized Eigen Space. So VI is all of V belongs to V such that the lambda minus X minus lambda I to identity to a power maybe mi0 and IV0. Okay, so now I can define SS to be SS on each VI, right? To be so okay, so notice that I can define SS to be lambda I VI to define to be just multiplication of lambda I. So if I have any vector U, I just map to lambda I times U. Okay, so you're easy to check that XS VI actually stabilize VI. Okay, so this is let me just quickly write down the proof. So proof is trivial because why is trivial? Okay, so if your XS on U and will be lambda IU, so it's the same as right. So definition is that times lambda IU, and you want to prove that it's still in VI, right? So that means I can act on X minus lambda I to the MI and the act on lambda IU. This is the same as X minus lambda I MI and XU, right? Because you can write this equation as X minus lambda I MI plus 1 U. Okay, so this is equal to 0, right? This is equal to 0. So if you expand it, then you will get expanded one term. You get XU equals to lambda IU. Okay. So which means that your XU, your XSU, lambda IU, your XSU is stabilized, right? Because if you use this, acting on this, then you will get these results, right? If you act on X minus lambda I and IXU, you'll get X minus lambda I equals to lambda I mu. Sorry, this is just the multiplication of lambda, so it's still in the VI. Okay, it's still in the VI. Okay, because simply speaking, or you just times lambda IU, right? So if original is negation by lambda, if X minus lambda I to the MIV 0, then any you just times a constant, and it's still inside. It's still if you times lambda I here, every time maybe times lambda IV, then you act on this guy is still 0. Yes, right, because you can pull out. Yeah, you can pull out this, right? Then you get 0, right? Because you pull out this lambda I, X minus I by U 0. Okay, so SSVI is fixed in VI. Okay, and now, so this means that XS is diagonalizable, right? It's diagonal in each VI, right? So in each VI, right? So SS basically is diagonal in each VI because in each VI always, each VI just times a lambda, right? So this is the same as in a Jordan form. Basically, suppose you have the first block. Let's say this is the first block, then this is the second block. Okay, maybe there's a up to k block. You take all the simply speaking, you can find basis. You take all the diagonal part. Okay, and so you take all this, and the rest are 0. This is basically the SS. That's it. Okay. Okay, so now we can define so we want to define xn, right? So which is the important part. So we define, and xn is defined to be trivial, to be defined to be just x minus ss. Okay, so notice that Sn is nilpotent. It's not difficult because let me see how do I see this. So because if you restrict it onto the spatial one block, right? This means that let's say you restricted this map into Vi. This is the same as what? This is the same as if you add on V, you will get XV minus SSV, right? But V satisfy this property. So V satisfy this property. So this means that X minus lambda is X minus lambda I to V. Okay, so which means that this map, this X map, time use X minus lambda I, just effectively as the same X minus lambda I. So Xn to the power Mi will be 0 by this. Okay, so this means that Xn is nilpotent on each block, right? So Sn is nilpotent. Okay, and okay, so simple calculation. You can easily check that SS and Sn is the same as Sn SS. Okay, so the proof is very simple. Right? Prove by yourself, right? Because I mean, if you can restrict it on each block, so this is X minus SS and SS, so it's you get SSX minus S squared or something like this, and you can try to prove it's X minus SSX, or is XSS minus XS squared. Okay, so now the final thing is to prove that XSS is actually SSS. This is easy to prove because you restrict it. If you restrict it on the subspace as on the Vi, then SS will be lambda I, right? So the left hand side will be just lambda Ix. Which is sorry. So we need to show this, right? Now we can do a restricting on the Vi. So you can see that this side, right? So this side maybe you want to add on X on Vi, right? So right, yeah, and this side we just times lambda I. So let's say the left hand side just lambda I X on Vi. Okay. And the right hand side will be SS on Vi. Okay, but X on Vi is a generalized eigenspace, right? So X on Vi will still be Vi, will still inside Vi, right? So when SXS on the subspace in Vi, then we will automatically just produce the lambda I X Vi. So you can see these two are the same. Okay. Right? So generalized, because the generalized eigenspace is still fixed by X. I think I don't need to, yeah, since the same proof, right? So the same proof. Let me see how to, yeah, so you take, let's say you take this is U, so you can take as U, and then maybe you do some X minus lambda I to the power N. You can prove it. So this guy is X minus lambda I M, and then the same as lambda I U, which you get 0. Okay, so done. Okay, so this will prove that the nilpotent. Okay, so I forgot to say about the final thing. So final thing is that this decomposition, this Jordan Chevalley decomposition is actually unique. Okay, so we just up to now we prove its existence, right? So finally we need to prove it's unique. So prove it's unique. this is trivial, right? Because okay, so the unique is trivial because let's say I can write this as two terms. Okay, and if I have these two decomposition, and let's say, so what I'm saying is that maybe previous is a spatial decomposition, right? Maybe there's another way that the other way that you can find out the other decomposition. But this is impossible, right? Because if this is true, then you can write as this. Okay. Okay. So so what? So now you got some stupid thing, right? So because this guy is generalizable, and this guy is important. Okay. So the only matrices which is semi-simple or diagonalizable and both important are 0. Okay. So the only matrices or the only operator matrices which is diagonalizable and the important is 0. Okay, so proof is very simple because you have diagonalizable, right? So you can write as this, and then it's important. Basically, all lambda will be 0. Okay, so now this is 0, this is 0. Okay, yeah, and by the way, so this is diagonalizable is trivial, right? You might worry that this is diagonalizable but in different bases, but since they're all commuting, right? So this means that this S by the way, so previous we already showed this, right? So SSN. So you also have this. So these SS and SS prime are both commuting with X. So they can be simultaneous diagonalizable with the eigen basis of X. So this is the reason why there are some bases such that these two guys are both diagonalizable and these two guys are obviously nilpotent. So in this case, that you can find some same base due to this commuting phenomenon. So this is why I can easily say that this guy is generalizable, this guy is important because they're all commuting with the original X, which we just proved. Okay, so yeah, so this is basically this is the region of Jordan form. Okay. Okay, so in the next video that I will describe why this generalized eigen basis decomposition is true. Basically, this is the heart of Jordan form, right? If you believe this is true, then sure you can easily prove it. See you guys next videos.